Hi, this is Stu Schwartz of MasterMathMentor.com. This is video Precalc 04A, and the topic is graphs of trig functions. You should see a table of special angles and quadrant angles from 0 degrees and 360 degrees. Set in your calculator to degree mode and 2 decimal places. Find the sine and cosine of these angles and complete the table. Notice how the values of the sine and cosine functions stay the same: 0, 1, or 0.5, 0.71, or 0.87. The only thing that changes are the signs, SIGNS. This is to be expected through our study of special angles and ASTC. Now, plot the points on the same graph. You may wish to plot them with 2 different color pens. These are the plots of the sine and cosine functions. The sine function in blue, the cosine function in red. Notice the sameness to them. The shape is pretty much the same. We then connect the dots with curves. It is not clear that we can do this, and you may want to take a look at different values between the special angles to confirm that the points will lie on these curves. We see the same shape, and we call these curves waves. We have the sine curve, which is a wave, and the cosine curve, which is a wave. In reality, they are both sine curves because the cosine curve has just been shifted. We will study this a little bit later in the section. So what we are seeing are the graphs of the sine and cosine functions. Now, since the function values will eventually repeat, we are looking at one cycle or one period of the curves. And we then call these curves periodic because of their repetitive nature. We can graph these using the calculator. For y1 equals sine of x, we set up a window while we are in degree mode, where x min is 0, x max is 360, and we'll use a scale of 30 degrees. We know that the minimum value of y is -1 and the maximum value of y is 1, and we'll use a scale of 0.1. And we see the graph of the sine function. We can also graph the cosine function using the same exact window. Let us now note the similarities and differences of the sine and cosine curves. For similarities, note that this shape is the same. Both curves are waves. And notice that both curves have a maximum value of 1 and a minimum value of -1. We know this in our study of the sine function and the cosine function from a previous chapter. However, there are some differences. The sine curve starts in the middle. Now realize that these curves continue forever in each direction, so there's no real starting. However, we mean by starting that at x is equal to 0, y for the sine curve is also 0. But for the cosine curve, it starts at the top, meaning that when x is 0, y is 1. Since these are periodic functions, we can look at as many periods as we want. So if we look at the sine curve, where x runs from -360 to 360, we will see 2 periods of the sine curve. And because the period of the cosine curve is also 360 degrees like the sine curve, if we let x run from 0 to 180, then we will see 3 periods of the cosine curve. If our calculator was in radian mode and we graphed the sine and cosine function, we would have to set x min to 0 and x max to 2 pi and a scale of pi over 2 with y min to be -1 and y max to be 1 to see exactly the same curves as we did in degree mode. It is important to know what mode you are in or your graphs will look very, very strange. When graphing functions on the calculator, we usually start with zoom 6 or zoom standard. That will set up the screen to be running from -10 to 10 and -10 to 10. We also have a zoom 7 trig, and we usually use these when we want to see a basic window for a trig function. When we are in degree mode and we hit zoom 7 trig, x min and x max are set to -352.5 and 352.5 with a scale of 90 and a y min of -4 and +4. When you are in radian mode and you do a zoom trig, the x min and x max are set to numbers close to -2 pi and pi, -6.15 and 6.15, with a scale of pi over 2 or 1.57. Y min and Y max are both -4 and 4. Just as the equation y equals mx plus b graphs a line, and changing m and b will change the slope and y-intercept of the line, we will find later in the chapter that there are many changes that will alter the features of the sine and cosine curve without altering the fact that it graphs a wave. All sine and cosine curves have 5 important points within one of its periods. We call these points critical points. These critical points are where the curve hits its high point, its low point, and its axis of symmetry, which is the horizontal line of which half of the curve is above and half is below. For the sine and cosine functions, we will find that the critical points are the same. If we are in radians, it is 0. If we are in degrees, it is 0 degrees. Next, pi over 2 or 90 degrees. Next, pi or 180 degrees. Next, 3 pi over 2 or 270 degrees. And finally, 2 pi or 360 degrees. So for the sine function, when x is 0 or 0 degrees, the sine of 0 or 0 degrees is 0, and thus our curve goes through the point 0, 0 or 0 degrees 0. So when x is pi over 2 or 90 degrees, the sine of pi over 2 or 90 degrees is 1. So the critical point for the high point is pi over 2, 1, or in degrees, 90 degrees, 1. When x is pi, or 180 degrees, the sine of pi, or 180 degrees, is 0. So we are back to the axis of symmetry, with our points either being pi 0 or 180 degrees 0. When x is 3 pi over 2 or 270 degrees, the sine of 3 pi over 2 or 270 degrees is -1. So we are at a low point, 3 pi over 2 negative 1, or 270 degrees negative 1. Finally, we are back to 2 pi, or 360 degrees, and the sine of 2 pi, or 360 degrees, is 0. So we're back to the axis of symmetry, and the last critical point is 2 pi 0, or 360 degrees 0. We do the exact same thing with the cosine curve, and you can see the results. The only difference is that while the sine curve starts at the axis of symmetry, then goes up, then back down to the axis of symmetry, then to its low point, and then back up to its axis of symmetry, the cosine curve starts at its high point, down to the axis of symmetry, down to its low point, then back up to its axis of symmetry, and then back up to its high point. But the critical points, at least the x values, stay the same. It may seem that the information presented in the next few minutes is off topic. I assure you it is not. Suppose a school district on the first day of classes measured the heights of all of its students. It then found the average heights of 6-year-olds, 7-year-olds, up to 18-year-olds, and plotted them on a graph with the age as the horizontal axis and the height on the vertical axis. The graph might look something like this, using lines to connect the points. However, there's no reason that the graph could not look like the one on the left or right. The reason is that the horizontal axis age is measured in years and the vertical height is measured in inches. They measure completely different things. And there is no one right way to determine the amount of horizontal space between two consecutive ages. So all three graphs give the same information and are accurate in showing the relationship between age and height. Now suppose the same school district also measured the waist of the students. And then, again, it averaged, for instance, the students who were 48 inches in height and looked at the average waist, students who were 51 inches in height and looked at the average waist size. We see three graphs that give the same information. Are all three a valid way of showing the data? There is a difference between the graphs in the blue above and these in red. The difference is that with height versus weight, both variables are measured in inches. So while all three graphs give the same information, someone looking at the middle graph might infer that as height increases, the weight increases very quickly. But looking at the scale shows that the height scale is 3, while the waist scale is 1, and that distorts the graph. The same is true with the first graph. The way to present the data without any distortion is to ensure that the horizontal scale is the same as the vertical scale. Notice how the small rectangle is a square, and with the scale of the two axes, as height increases by 1, so does the waist. So there is no distortion here, and this is the most accurate way to present the data. Still, there are occasions that we may not have enough room to present the data without any distortion. For instance, to create a graph showing the distance of a planet from the sun in miles versus the diameter of the planet in miles, there is no way to do it without tremendous distortion, as the distance values are so large relative to the diameter values. So keep this in mind when we graph trig functions. So by the same argument, the graphs of y equals sine of x in blue and y equals cosine of x in red are accurate at any of these three examples, where x on the horizontal axis is measured in degrees. X is an angle and y is a number. And like age and height, they are measured in incompatible units if we are using degrees. So there is no one right way to depict them. When you graph, you decide based upon how much horizontal or vertical space you have. Realize, though, that degrees are man-made, created for convenience. Angles are truly expressed in radians, which have no units. They are pure numbers, just as are the sine and cosine of angles. So when graphed, we can graph them to scale, with one unit on the x-axis, representing the same distance as on the y-axis. So what you see is the sine and cosine curve scaled correctly. Notice that once you decide the height of your curve, which is 1, the x-axis should be 2 pi, or a little bit more than 6 times as wide. Using the same proportions as we did above, we now show the critical points that occur at 1/2 pi, pi, 3/2 pi, and 2 pi. So this is more convenient in terms of giving important information about the graph, and it is generally what we use. This is a graph of the sine function and cosine function scaled perfectly. Still, realize that when we graph, it is much more convenient to graph using degrees on the x-axis, where there is no one right way to show it. For the rest of the unit, that is what we will do, and we will create our graphs based on available room. Just be aware that if you want your graph to be to scale, that whatever distance is 1 on the y-axis, then 360 degrees should be about 6 times that distance on the x-axis, as shown. Now that we know the shape and behavior of the sine and cosine curves, we will now do some things to alter that behavior. Our goal is to predict the shape of the curve without resorting to actually graphing it by plotting points. So on our calculators, we will be graphing the curves y equals sine of x, y equals 2 sine of x, y equals 4 sine of x, y equals negative 3 sine of x, and y is equal to negative 0.5 sine of x, while x is in degree mode. We see our basic y equals sine of x curve in blue. Y equals 2 sine of x is in red. Notice that it is stretched twice as high and twice as low as y equals sine of x. But the critical points along the axis stays the same. In y equals 4 sine of x in green, the curve is stretched to 4 times its height and 4 times its depth. We are changing the curve's scaling factor, a vertical stretch of the curve. We call this the amplitude, which is the height of the curve above its axis of symmetry. So for y equals sine of x, its amplitude is 1. Y equals 2 sine of x, its amplitude is 2. Y equals 4 sine of x, its amplitude is 4. In y equals negative 3 sine of x in orange, several changes occur. First, the height of the curve above its axis of symmetry is 3, which becomes the curve's amplitude. But instead of the curve going up at first, it goes down. We call this reversing the curve. So in y is equal to negative 0.5 sine of x in purple, the curve 2 is reversed. And now it is no longer stretched, but shrunk vertically. The curve reaches 0.5 above its axis of symmetry, so its amplitude is 0.5. So we now have some general rules for the curves in the form of y equals a sine of x or y equals a cosine of x. We define the amplitude of those curves as the largest possible value of y and is given by the absolute value of a. Amplitude is always a positive number because we know it represents the height of the curve above its axis of symmetry. That means that the range, which is the allowable y values of the curve, is from negative, the absolute value of a, to the absolute value of a. We will define the shape of the curve using this generalization. If a is greater than 0, we say that the curve is normal. But if a is less than 0, then we say that the curve is reversed. And then finally, we define vertical change using this set of information. If the amplitude is greater than 1, we say that the curve is vertically stretched. If the amplitude is less than 1, then we say that the curve is vertically shrunk. And if the amplitude is equal to 1, that means that there is no vertical change. Let's see how this works on a number of curves. So in example 1, we are given 6 curves, and we are to find the amplitude, the range of the function, the 5 critical points in degrees, and then you should graph it on your calculator using an appropriate window to verify the behavior of the graph that you just found. In A, we have y equals 3 cosine of x. The amplitude is the absolute value of the coefficient of the cosine function, and that is 3, making the range negative 3 to 3. Our critical points are 0, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. The shape is normal because the coefficient of the cosine function is positive, and vertically the curve is stretched because the amplitude is greater than 1. In B, we have y is equal to negative 2 sine of x. The amplitude is 2, as that is the absolute value of negative 2, making the range negative 2 to 2. Our critical points are still 0, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Our shape now is reversed because of the negative 2, and vertically the curve is stretched because the amplitude is greater than 1. In C, we have y is equal to cosine of x. The amplitude is the coefficient of the cosine function, which is 1, making the range negative 1 to 1. The critical points are still 0, 90, 180, 270, and 360 degrees. The shape of this is normal, and there is no vertical stretch or shrinkage because of the amplitude being 1. In D, we have y is equal to 7 sine of x. Our amplitude is 7, and therefore our range is negative 7 to 7. Critical points haven't changed to 0, 90, 180, 270, and 360. This curve is normal, and it is vertically stretched. In E, we have y is equal to 2/3 sine of x. Our amplitude is 2/3, and our range is negative 2/3 to 2/3. Critical points still haven't changed, 0, 90, 180, 270, 360. The shape of this curve is normal, and vertically this curve is now shrunk. Finally, in F, y is equal to negative pi cosine of x. Our amplitude in this case is pi. The range is negative pi to pi. Critical points are still 0, 90, 180, 270, and 360 degrees. The shape of this curve is reversed, and vertically the curve is stretched as pi is greater than 1. Here we see the graph of y is equal to sine of x, where x is measured in degrees, and it is not to scale. We see one cycle of the sinusoid within 360 degrees. So the period is 360 degrees, or 2 pi if we measure in radians. Next, we see three other curves as compared to y is equal to sine of x. We see y is equal to sine of 2x in red, y is equal to sine 4x in green, and y is equal to sine of 1/2 x in purple. Notice that we are not seeing now one cycle of the sinusoid, but other numbers of cycles. Let's see if we can come up with what is going on. In y is equal to sine of 2x in red, we are getting two cycles of the sinusoid within 360 degrees. So the period of y is equal to sine of x must be 180 degrees, or pi in radians. This means that compared to the graph of y is equal to sine of x in blue, the graph of y is equal to sine 2x is compressed. In y is equal to sine of 4x in green, we are getting four cycles of the sinusoid within 360 degrees. That means that the period of y is equal to sine of 4x is 90 degrees, or pi over 2 radians. Compared to y is equal to sine of x, this curve is compressed. For y is equal to sine of 1/2 x in purple, we are getting 1/2 of the cycle of a sinusoid within 360 degrees. That means that the period of y is equal to sine of 0.5x must be 720 degrees, or 4 pi radians. So compared to y is equal to sine of x in blue, the graph of y is equal to sine of 1/2 x is elongated. So we come up with our next generalization that deals with period. The period of y equals sine of bx, or y equals cosine of bx, is the number of degrees or radians the curve takes to complete one cycle. It is found using this formula. The period is 360 degrees divided by b, if we are working in degrees, or 2 pi divided by b, if we're working in radians. Our goal in this section is to not actually have to graph these equations, but to be able to describe them. So, when describing the graph of y is equal to sine of bx, or y is equal to cosine of bx, we are comparing it to our regular curve y is equal to sine of x, or y is equal to cosine of x. And we will define the horizontal stretch in words. If the period is less than 360 degrees, or 2 pi measured in radians, we say that the graph is compressed compared to y equals sine of x or y equals cosine of x. If the period is greater than 360 degrees, or 2 pi, then we say our graph is elongated. And if our period is equal to exactly 360 degrees, or 2 pi, that means that there is no horizontal stretch. Realize that if the period changes, so do our critical points. Instead of using 0, 90, 180, 270, and 360, the critical points will now be 0, 1/4 of the period, 1/2 the period, 3/4 of the period, and the period, whether we're measuring in degrees or radians. There is an easy way to find these. First, we find the middle critical point first, which is half of the period. The second critical point will be half of that number. And the fourth critical point will simply be the sum of the second and third critical points. Let's suppose we have a curve with a period of 480 degrees. That means the first critical point will be 0 degrees, and the final critical point will be 480 degrees. So the middle critical point must be 1/2 of the period, or 240 degrees. The second critical point must be 1/2 of 240 degrees, which is 120 degrees. And the fourth critical point will simply be 3/4 of 480, or better, 120 plus 240 to get 360 degrees. In example 2, we have 7 different curves, and we would like to establish the period, determine the horizontal stretch, and also the critical points. In A, we have y is equal to cosine of 2x. The period, therefore, is 360 over 2, which is 180 degrees. Since this is less than 360 degrees, the curve is compressed. The critical points will be 0 degrees and 180 degrees, 90 degrees in the middle, 45 degrees in the middle, and then 135 degrees in the middle. For B, y equals sine of 3x, the period is 360 degrees divided by 3, which is 120 degrees. Since this is less than 360, this is also a horizontal compressed. And the critical points are 0 and 120 degrees at the ends, 60 degrees in the middle, and then between the 0 and 60 we have 30, between the 60 and 120 we have 90 degrees. For C, y is equal to cosine of 4x, our period is 360 degrees divided by 4, or 90 degrees. This is less than 360, so the curve is compressed. And the critical points will be 0 and 90 at the extremes, 45 degrees in the middle, and as the second one we will have 22.5 degrees, and the fourth one 67.5 degrees. For D, y is equal to sine of 1/2 x. The period is 360 degrees divided by 1/2, which is 720 degrees. This is greater than 360 degrees, so the curve is elongated. The critical points will be 0 and 720 at the extremes, 360 degrees in the middle, and then the second one is 180 degrees, and the third is 180 plus 360, or 540 degrees. For E, y is equal to cosine of 2/3 x. Our period is 360 degrees over 2/3, which is 360 degrees times 3/2, which is 540 degrees. This is greater than 360 degrees, so our curve is elongated. Our critical points will be 0 and 540 at the extremes, 270 in the middle, 135 as the second, and 405, which is the sum of 135 and 270. In F, we have y is equal to sine of 3/2 x. The period is 360 degrees divided by 3/2, which is 360 degrees times 2/3, or 240 degrees. This is less than 360 degrees, making the curve compressed. The critical points are 0 and 240 at the ends, 120 degrees in the middle, 60 degrees between 0 and 120, and 60 plus 120, which is 180 as the fourth critical point. Finally, for G, we have y is equal to cosine of 10x. The period is 360 degrees divided by 10, which is 36 degrees. Since this is less than 360 degrees, this will be compressed, very compressed, because the period is so small. The critical points will be 0 degrees, 36 degrees at the ends, 18 degrees in the middle, 9 degrees between 0 and 18, and 9 plus 18, which is 27 degrees as the fourth critical point. In example 3, we're going to put everything together, the amplitude and the period. So for each of the curves, we want to find the amplitude, the period, the critical points, and then the shape, whether it's normal or reversed, the vertical stretch, whether it's stretched, shrunk, or neither, and the horizontal stretch, whether it's compressed, elongated, or neither. In A, we have y is equal to 2 sine of x. The amplitude is the coefficient of the trig function, which is 2. The period is 360 degrees divided by the coefficient of x, and that is 360 degrees divided by 1, or 360 degrees, giving our normal critical points of 0, 90, 180, 270, and 360 degrees. This curve is normal. Because of the amplitude being 2, the curve is stretched vertically, and there is no horizontal stretch because the period is 360 degrees. In B, we have y equals sine of 2x. Here our amplitude is the coefficient of the sine, which is 1, and the period is 360 degrees divided by 2, or 180. Making the critical points 0, 45, 90, 135, and 180. Again, this is a normal curve. It is neither stretched nor shrunk because the amplitude is 1, and the curve is compressed because the period is 180 degrees. In C, we have y is equal to 2 sine of 2x. The amplitude is 2 because of the first 2. The period is 360 degrees divided by the coefficient of x, which is 2, and that gets us to 180 degrees. The critical points are, as we saw above, 0, 45, 90, 135, and 180. This is a normal curve. It is stretched because the amplitude is 2, and it is compressed because the period is less than 360 degrees. In D, we have y is equal to 4 cosine of 3x. Our amplitude is 4. Our period is 360 degrees divided by 3, or 120 degrees, making the critical points 0, 30, 60, 90, and 120 degrees. This curve is normal, and it is vertically stretched because of the amplitude being 4, and it is compressed because the period is less than 360 degrees. In E, we have y is equal to negative 3 cosine of 6x. Our amplitude is the absolute value of negative 3, which is 3. Our period is 360 degrees divided by 6, which is 60 degrees, making our critical points 0, 15 degrees, 30, 45, and 60 degrees. Because of the negative, this curve is reversed. Because the amplitude is greater than 1, it is vertically stretched, and because the period is less than 360 degrees, this curve is compressed. In F, we have y is equal to 1/2 sine of 1/2 x. The amplitude is the first 1/2. The period is 360 degrees divided by 1/2, which is 720 degrees. That makes the critical points 0, 180, 360, 540, and 720 degrees. This curve is normal. In terms of the vertical stretch, it is shrunk because the amplitude is less than 1. And this curve is also horizontally elongated because the period is greater than 360 degrees. For G, y is equal to sine of 4/3 x. The amplitude is the coefficient of the sine function, which is 1. The period is 360 degrees divided by 4/3, which is 360 degrees times 3/4, or 270 degrees, making the critical points 0, 67.5, 135, 202.5, and 270 degrees. This curve is normal. There is no vertical stretch or shrinkage, and in terms of the horizontal stretch, since the period is less than 360 degrees, it is compressed. H reads y is equal to negative 3/4 sine of 3/4 x. The amplitude is 3/4. The period is 360 degrees divided by 3/4, which is 360 degrees times 4/3, or 480 degrees, making the critical points 0, 120 degrees, 240 degrees, 360 degrees, and 480 degrees. This curve is reversed because of the negative sign. Because the amplitude is less than 1, this curve is vertically shrunk, and because the period is greater than 360 degrees, this curve is vertically elongated. We have stretched and shrunk our curves vertically and horizontally. We can also move the entire curve up or down, or right or left. These are called translations. So on the graph, we see y is equal to sine of x in blue, y is equal to 2 plus sine of x in red, and y equals negative 1 plus sine of x in green. What we see is that the red curve is the blue curve shifted 2 units up, and the green curve is the blue curve shifted 1 unit down. Again, we will call these vertical translations. So any curve in the form of y is equal to d plus or minus a sine bx, or y is equal to d plus or minus a cosine of bx, will shift our curves. Y is equal to plus or minus a sine bx, or y is equal to plus or minus a cosine bx, up or down based upon the value of d. This is called the vertical translation of the curve. So if d is positive, we have a vertical translation up d units. If d is negative, then we have a vertical translation down the absolute value of d units. And if d is equal to 0, just as we saw with y is equal to sine of x, there is no vertical translation. So now let us look at y is equal to sine of x in blue. Y is equal to sine of quantity x minus 30 degrees in red, and y is equal to sine of quantity x plus 45 degrees in green. Our blue curve is our regular sine curve. Notice though that our red curve, y is equal to sine of quantity x minus 30 degrees, takes our blue curve and shifts it 30 degrees to the right, while y is equal to sine of x plus 45 degrees takes our blue curve and shifts it 45 degrees to the left, getting the green curve. So a curve in the form of y is equal to sine of quantity x minus c, or y is equal to cosine quantity x minus c, will shift the sinusoid right or left based upon the value of c. This value of c is called the phase shift, or sometimes the horizontal translation. If c is a positive number, the curve shifts right. So y is equal to sine of quantity x minus 10 degrees is going to shift the curve right, because the formula that we were given above assumes a minus sign. If c is less than 0, the curve shifts left. So y is equal to sine of quantity x plus 10 degrees is going to shift the curve left. In reality, since the formula involves negatives, then it's sine of x minus negative 10. However, you may want to just think that if it's a negative sign, it shifts right, a positive sign shifts left, which is a little bit different than the way you might normally think it will work. Now, when there is a phase shift or horizontal translation, the critical points are going to change as well. And I like to call these the true critical points. So we find the critical points without any translation and then add or subtract the phase shift C to get the true critical points. So if our critical points are 0, 1/4 of the period, 1/2 the period, 3/4 of the period, and the period, then the true critical points will add on the value of C to each of them, getting C, 1/4 the period plus C, 1/2 the period plus C, 3/4 of the period plus C, and the period plus C. In example 4, you are given 5 curves. You are to determine the vertical translation, the phase shift, including the direction, the critical points, and then the true critical points. In A, we have y is equal to 4 plus sine of x. The vertical translation is 4. The phase shift doesn't exist because there is no parentheses around the x. Therefore, the true critical points are 0, 90, 180, 270, and 360 degrees. In B, we have y is equal to cosine quantity x minus 60 degrees. There is no vertical translation. The phase shift is 60 degrees right. So since our critical points are 0, 90, 180, 270, 360, adding 60 degrees to each of those gives 60 degrees, 150 degrees, 240 degrees, 330 degrees, and 420 degrees. In C, we have y is equal to 5 plus sine of quantity x plus 20 degrees. Our vertical translation is 5 units up, and our phase shift is 20 degrees to the left. Again, our critical points are 0, 90, 180, 270, and 360, and subtracting 20 degrees from each, we get negative 20, 70, 160, 250, and 340 degrees. In D, we have y is equal to negative 2 minus cosine of quantity x plus pi over 6. Our vertical translation is 2 units down, and since we are in radians, then our phase shift direction is 6 pi over 6 left. In radians, our critical points are 0, pi over 2, pi, 3 pi over 2, and 2 pi. So we have to subtract pi over 6 from each of those, getting negative pi over 6, pi over 3, 5 pi over 6, 4 pi over 3, and 11 pi over 6. In E, we have y is equal to sine quantity x minus pi over 4 minus 1. Sometimes we do not put the vertical translation first. In this case, we put it at the end. This is 1 unit down, and the phase shift is pi over 4 right. So our critical points are 0, pi over 2, pi, 3 pi over 2, and 2 pi, and therefore adding pi over 4 to each, we get pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and 9 pi over 4. Obviously, you need to be able to work with fractions when you're working in radians. So let's put it all together. We are working with the equations y is equal to d plus or minus a sine of b quantity x minus c, or y is equal to d plus or minus a cosine of b quantity x minus c. Our goal is to use the values of a, b, c, and d, plus any signs involved, to give a full description of the behavior of the curve. We first look at the variable a. The amplitude of the curve, the height of the curve above its axis, is the absolute value of a. We then define the shape of the curve using this rule. If a is positive, we describe the curve as normal, but if a is negative, we describe the curve as reversed. The vertical stretch is dependent upon a, okay, the amplitude. If the amplitude is greater than 1, then we say the curve has been vertically stretched. If the amplitude is less than 1, then we say that the curve has been vertically shrunk. We next look at the variable b. b is used to determine the period. If we are working in degrees, then the period is 360 degrees divided by b. If we're working in radians, then the period is 2 pi divided by b. And therefore, the horizontal stretch is dependent upon the period. So if the period is less than 360 degrees, or 2 pi in radians, we describe the horizontal stretch as compressed. And if the period is greater than 360 degrees, or 2 pi in radians, we describe the horizontal stretch as elongated. We next look at the variable c. c controls the phase shift, or sometimes called the horizontal translation. Remembering that the equations use the parentheses x minus c. If c is positive, then the curve shifts right. If c is negative, then the curve shifts left. And therefore, the critical points are dependent upon the period and c. So the critical points are 0, 1/4 the period, 1/2 the period, 3/4 of the period, and the period. And therefore, the true critical points will add on the value of c. So it's c, 1/4 the period plus c, 1/2 the period plus c, 3/4 the period plus c, and the period plus c. Finally, the variable d. d controls the vertical translation. If d is a positive number, then the vertical translation is up d units. If d is a negative number, then the vertical translation is down the absolute value of d units. Therefore, the range of the function is simply from d minus a to d plus a. In the past, students would be asked to graph these on graph paper. Very tedious work. We know that calculators can graph them. So now you are simply being asked to describe all aspects of the curves without actually plotting the points. So for each curve, you are to find all pertinent information, then verify it on your calculator. The way you do this verification is to input the function and then graph it. Your x-min and x-max should be the smallest and largest of the true critical points. Your y-min and y-max should be the smallest and largest values of the range. And if your answer is correct, you will see exactly one period of the curve. A reads y equals 3 minus cosine x. The coefficient of the cosine function is -1, so the amplitude is 1. The coefficient of the x is 1, and therefore the period is 360 degrees. There is no phase shift, so the critical points and true critical points are 0, 90, 180, 270, and 360. This curve has been shifted 3 units up, and therefore the range runs from 2 to 4. This is a reverse curve because of the negative sign, and it is neither stretched nor shrunk, and it is neither compressed nor elongated. Here is the verification. We won't verify every problem, but here is the process. We've set x min to 0, x max to 360, y min to 2, y max to 4. And when we graph the curve, we see one period of the cosine curve, and in this case, the cosine curve is reversed. In B, our curve is y is equal to 1 plus 2 cosine of 2x. Our amplitude is 2, our period is 360 over 2, which is 180 degrees. With no phase shift, our true critical points are 0, 45, 90, 135, and 180 degrees. Our curve has been translated one unit up, and therefore our range is from -1 to 3. The shape is normal. Because we have an amplitude of 2, the curve has been stretched vertically, and because the period is less than 360 degrees, the curve is compressed horizontally. In C, we have y is equal to -2 minus 3 sine of 4x. The amplitude is 3, the period is 360 degrees divided by 4, or 90 degrees. There is no phase shift. So the true critical points are 0, 22.5, 45, 67.5, and 90 degrees. This curve has been translated 2 units down, so the range is -5 to 1. The shape of this curve is reversed because of the negative sign. It is stretched vertically because of the amplitude of 3, and it has been compressed horizontally because of the period less than 360 degrees. In D, we have y is equal to 5 sine of quantity x minus 30 degrees. The amplitude is 5, the period is 360 degrees, and it's been shifted 30 degrees to the right. So our critical points are 0, 90, 180, 270, 360, making the true critical points 30, 120, 210, 300, and 390 degrees. There is no vertical translation, and the range is from -5 to 5. This curve is normal. Because the amplitude is greater than 1, this curve is vertically stretched, and because the period is exactly 360 degrees, the curve is neither compressed nor elongated. In E, we have y is equal to -1 minus cosine of quantity x plus 15 degrees. The amplitude is 1, and the period is 360 degrees. The phase shift is 15 degrees to the left. So since our critical points are normal, 0, 90, 180, 270, 360, shifting to the left gives us -15 degrees, 75 degrees, 165 degrees, 255 degrees, and 345 degrees. The vertical translation is 1 unit down, so the range is from -2 to 0. This curve is reversed because the amplitude is 1, it's neither vertically stretched or shrunk, and because the period is 360 degrees, it is neither compressed nor elongated horizontally. In F, we have y equals 2 plus 1/2 sine of 2 times the quantity x minus 5 degrees. The amplitude is 1/2, the period is 360 over 2, or 180 degrees, and the phase shift is 5 degrees to the right. So our critical points are 0, 45, 90, 135, and 180 degrees. When we shift to the right, we get 5, 50 degrees, 95, 140, and 185 degrees. This curve vertically has been shifted 2 units up, making the range 1.5 to 2.5. The curve is normal because the amplitude is less than 1. It is vertically shrunk, and because the period is less than 360 degrees, it is horizontally compressed. G reads y is equal to 1/2 minus 4 cosine quantity 3x plus 15 degrees. This problem contains a trap. Since our general form is y is equal to d plus or minus a cosine of b quantity x minus c degrees, we have to factor the 3 out to get y is equal to 1/2 minus 4 cosine of 3 quantity x plus 5 degrees. Now it is in the correct format. The amplitude is 4 and the period is 360 divided by 3 or 120 degrees. It has been shifted 5 degrees to the left. So our critical points are 0, 30, 60, 90, and 120 degrees. And therefore the true critical points are -5, 25, 55, 85, and 115 degrees. The curve has been shifted 1/2 unit up, making the range -3.5 to 4.5. The curve is reversed. Since the amplitude is 4, it is vertically stretched, and since the period is less than 360 degrees, it is compressed. In H, reading -3/4 sine of 1/2 x minus 40 degrees, we have to factor out the 1/2, and we get y is equal to -3/4 sine of 1/2 quantity x minus 80 degrees. That means that the amplitude is 3/4, the period is 360 divided by 1/2 or 720, and the curve has been shifted 80 degrees to the right. So our critical points are 0, 180, 360, 540, and 720 degrees. Shifting, we get 80, 260, 440, 620, and 800 degrees. There is no vertical translation, making the range -3/4 to 3/4. The curve is reversed, and because the amplitude is less than 1, the curve is vertically shrunk, and because the period is greater than 360 degrees, it is elongated. Let's verify this one. We set up our graph window with x min to be 80, x max to be 800, y min to be -0.75, and y max to be 0.75. And when we graph our curve, we see that it is reversed, and it takes up the entire window. Finally, in I, we have y is equal to 5 plus 3 sine quantity 2x minus pi over 2. We factor out the 2, and we get 5 plus 3 sine of 2 quantity x minus pi over 4. The amplitude is 3, and since we are in radians, the period is 2 pi divided by 2, or pi. We have a phase shift of pi over 4 to the right. So the critical points are 0, pi over 4, pi over 2, 3 pi over 2, and pi, making the true critical points pi over 4, pi over 2, 3 pi over 4, pi, and 5 pi over 4. This curve has been shifted 5 units up, making the range 2 to 8. It is normal, and since the amplitude is greater than 1, the curve is vertically stretched, and since the period is less than 2 pi, it is horizontally compressed. Make sure you watch video 04B for the second half of this section. We will reverse the process and generate an equation from a graph rather than describing a graph from the equation. We will then be able to generate a sinusoid from 5 points. And finally, we will look at applications of sinusoids when we study harmonic motion.